So I will be talking about resource allocation optimization on the max weight / back pressure algorithm. There are many ways one can explain the max weight or back pressure algorithm. I will try to explain it using an optimization viewpoint. Okay, so you could also come at it from a stochastic networks viewpoint. You could approach it from a control theory viewpoint. So today I'm going to approach it from an optimization viewpoint. And the only thing I think you would need to understand this talk, maybe I've dumbed it down too much, but the only thing you would need to know is what is a Lagrange multiplier. So if you know what a Lagrange multiplier is, I should be able to explain what the back pressure algorithm is to you. Okay. So I've already mentioned that. So the connection between the focus of this talk will be on connection between convex optimization, Lagrange multipliers, and the max weight back pressure algorithm. The back pressure algorithm was originally sort of discovered in 1992 by Tasioulis and Ephremides, but this connection between optimization and this algorithm was uncovered around 2005 by a number of us in parallel. So this is slightly old work, what I'm going to talk about. The rest of the speakers will be talking about more interesting things, which are connections to data centers, connections to ride sharing, connections to crowdsourcing, and many other, and machine learning, and so on. So I'll give the boring part of the talk. Then if you wait around, the next 3 talks will be more interesting. Okay. So I am going to motivate the talk using 3 applications. Traditionally, the back pressure algorithm came out of a desire to design resource allocation algorithms for wireless networks. So I will start off with that historical motivation and derive the algorithm for that particular setup. And then I'll talk about 2 other applications for ad placement and in the context of virtual machines. The virtual machine example is an example where it doesn't work as well. So that's sort of an illustration of an open problem, possibly. Okay. And as I said, this work builds upon the work of a lot of different people. The original algorithm was derived by Tasioulis and Ephremides in around 2005. A number of us came at it in different ways, and Lin and Schroff looked at the connection between optimization and the max weight / back pressure algorithm. Neely and Modiano and myself and Attila Ariel-Mas and Sasha Stoliar, we looked at it both from an optimization perspective and a stochastic networks perspective. And a bit later than that, I looked at the online advertising problem and with Bo Tan, who is now the head of pricing for DD Labs. So I'll briefly talk about that. And then with Sivateja, who's one of the speakers here, and Lei Ying, we looked at virtual machine placement, which is another application, but where it doesn't work very well. I mean, I want to sort of point out the limitations of the algorithm as well, and so that's the last example. Okay, so let's, and please feel free to stop and ask me questions anytime, okay? So let's talk about wireless networks first. So the context in which the back pressure algorithm was originally derived was you have in the context of wireless networks. So you have a wireless network, and links in a wireless network interfere with each other. So when this radio is transmitting to this radio, this transmission will not be possible, and this transmission will not be possible, for example. Okay? So any link, of course, these are directional links. I haven't shown the direction, so this could be, for example, you might be transmitting from here to here or from here to here. But in any case, activating any of these directed links will deactivate some of the links around it. Okay? In other words, or if somebody else also tries to talk at the same time in the vicinity, then neither transmission will be successful. Okay? So the goal is to figure out which links to activate each time instant. Okay? So in other words, in the language of networking protocols, you want to design a network protocol stack that decides which links to activate at each time instant. And as I mentioned, the problem is that links interfere with each other. So the back pressure algorithm, or the max weight algorithm, is one way to decide which links should be activated. Okay? What I want to address here is a very interesting and fundamental problem, which is the resulting algorithm is not computationally feasible at all. Okay? So it turns out that it's in the context of, in the applications in the context of data centers, for example, you have to solve a max weight matching problem, which at least is polynomial time. Okay, but even that is not feasible when you're talking about a bipartite graph with where the number of nodes is 10,000. As we'll see, you have to solve a max weight matching on a bipartite graph, which is again certainly what's n square log n. Is definitely you can't do it every time slot. You cannot keep changing the schedule by solving a max weight matching problem, even though it's a relatively simple polynomial time solution exists. But in the context of wireless networks, it turns out that it's a max weight independent set problem, which of course you can't solve. And so there's a completely parallel line of work which talks about how to come up with low complexity distributed implementations of max weight algorithms. And in some cases, can you come up with approximate solutions that have some provable performance guarantees and so on. But I'm not going to talk about that here. Okay, so just let me state that. So I'm just only going to derive the max weight algorithm from an optimization perspective. Okay? And I don't think anybody is going to address the computational complexity issue in today's talk, but that is a very, very important problem that is not being addressed in the 4 hours today. Okay? Okay. So I'm going to take a very, very simple example to illustrate the algorithm, and hopefully this will convey much of the insight behind how the algorithm is derived. So taking an example where there are 2 links, link A and link B. Each link can transmit 1 packet per second, 1 packet per time slot. Time is assumed to be slotted. Each link can transmit 1 packet per time slot. However, if this link is active, this link cannot be active because they're right next to each other and they interfere with each other. Okay? There are 2 users in this network. There is a user which wants to transmit packets from this node to this node, and there's another user which wants to transmit packets from this node to this node. So the fact that the 2 links cannot transmit simultaneously means that the 2 users cannot also transmit simultaneously. Okay? In general, the users and links could be separate things. A user could take multiple hops to reach its destination and so on. But in this very simple model, each user is associated with 1 link, just for simplicity. Okay? So you have to decide which link should be activated each time. So that's the problem. Okay? Of course, in this very simple case, you can probably solve it. I mean, once I tell you a little bit more, you can solve it explicitly. But I want to derive the max weight algorithm for this simple setup where everything is obvious. Okay? Okay. How do you decide which link to activate? So you have to somehow set up an optimization problem. So what I'm going to assume is that associated with each user is the rate at which it's transmitting. X1 is the rate at which user 1 is transmitting. X2 is the rate at which user 2 is transmitting. In other words, X1 is measured in packets per time slot. X2 is measured in packets per time slot. And there is a utility associated with transmitting at a certain rate. So you can think of this utility as a concave increasing function, sort of like log, for example, is a good example. Okay? So log is, if you use log as a utility function, this gives the Nash bargaining solution or proportional fairness or whatever you want to call it, right? So you can have any utility function here. And so the goal is to maximize the sum of the utilities of all the users. And what do you control? What you control is each user controls how many packets it's putting into the system. So that's X. And what the network controls is that the rate at the fraction of time link A is active and the fraction of time link B is active. Okay? So the network controls the fraction of time this link is active, fraction of time this link is active, and the users control the rate at which they're pumping packets into this network. Of course, simple flow conservation dictates that the rate at which packets are generated by user 1 must be less than or equal to the fraction of time that link A is active. Otherwise, the system will not be stable. Arrival rate must be less than or equal to departure rate. Right? So similarly, X2 must be less than or equal to mu B. So this is a standard convex optimization problem. So it's a relaxation because I'm going to assume that the fraction mu A plus mu B is less than or equal to 1. Whereas in reality, what you need is at each time step, you need to make sure that either link A is active or link B is active. So this is a relaxation of the original problem. But we'll see that this relaxation doesn't matter, and you'll get a solution where only one of the 2 links is active. Is the optimization problem clear? So more generally, you'll have a number of users. You're trying to maximize the system-wide utility, which is maximize the sum of the utility of all the users, subject to the constraint that what each user generates must be handleable by the network. Okay, and this last thing is interference constraint. Okay, very simple setup. So how would we solve an optimization problem? Constrained optimization problem. What would we do? We use Lagrange multipliers and take the constraints and add it to the objective. That's it, right? So what I'm going to do is I'm going to take these two constraints and add it to the objective using Lagrange multipliers, but leave the last constraint alone. Turns out that turns out to be the best thing to do in this case, and you'll see why in a second. Okay, so I'm going to take x1 less than or equal to mu a and x2 less than or equal to mu b, add it to the objective to get a new optimization problem to where this is where you have a Lagrangian instead of the original objective. Now I have this new problem. Okay, now here something beautiful happens. So this optimization is over x and mu, right? The optimization over x and the optimization over mu separate if you know the p's. If you know the Lagrange multipliers, let's for the moment assume the Lagrange multipliers are known, then the optimization over x and the optimization over mu separate, right? So basically you have an optimization problem over x and an optimization problem over mu. And the optimization problem over x, in fact, further separates into optimization problems over each individual x. So each user, if the Lagrange multipliers are known, each user can decide the rate at which they have to transmit by simply solving this optimization problem where they have the utility minus the cost of transmitting at rate x1. Okay, so this is often called congestion control in the networking literature. So you're deciding the rate at which you're transmitting based on the cost of using the link, which is P1 or P2, or PA or PB. That should be PA or PB. Yeah, I think I messed up the notation. Did I use? Okay, I guess I used P1, P2, previous page too. Anyway, so the optimization problem over mu's also separate. So the optimization over mu's become maximized P1 mu A plus P2 mu B. Okay, subject to the constraint that mu1 plus mu2 is less than or equal to 1. Well, clearly the solution to this problem is an extreme point. So you will either activate link 1 or activate link 2. Is this clear? So this relaxation hasn't affected us. Okay. So the only remaining thing that we need to figure out is how to compute the Lagrange multipliers. Okay. Oh, by the way, this is called the max-weight algorithm. So the max-weight algorithm basically says that associate a weight with each link. In this case, the weight is simply the Lagrange multiplier of that link, and solve an optimization problem. And the solution to this optimization problem will always be an extreme point, right? So it'll satisfy the inherent physical constraint that we started out with. How do you compute? So the final thing that we have to figure out is how to compute the Lagrange multipliers. So we have a constraint of the form x1 less than or equal to mu a. Okay? So the dual algorithm for computing the Lagrange multiplier says, so I switched, sorry, I use PA and P1 sometimes. So PA at time k plus 1 is PA at time k plus some step size multiplied by the left-hand side minus the right-hand side. And you can interpret it as a dual algorithm. You can write the dual, and this is just simply the dual descent algorithm. Or if you don't even want to think about it that way, this is just simply saying that PA is just simply the cost of using link A. And so if the left-hand side is less than the right-hand side, that means that you're not violating the constraint, so you can reduce the cost further. So you can encourage users to transmit at a higher rate. So if x1 is less than mu, you should decrease the price. If x1 is larger than mu, sorry, if x1 is less than mu, you should decrease the price, correct? And if x1 is larger than mu, you should increase the price because you're violating the constraint. So therefore, you should reduce the value of the Lagrange multiplier. But what does this look like? So this is just simply the x1 is the rate at which user 1 is transmitting packets. Mu a is the fraction of time link A is activated. So this is essentially the queuing behavior of link 1. So the queue length at time k plus 1, if you divide the whole thing by epsilon, the queue length at time k plus 1 is the queue length at time k plus new arrivals minus departures. So what this is saying is that you don't even need to compute the Lagrange multipliers. The network naturally computes the Lagrange multipliers for you. Okay, so the network naturally computes the Lagrange multipliers for you. There's nothing you have to do. So it turns out this is a lot of the solution becomes very simple. Each user can calculate the rate at which it has to transmit by knowing its Lagrange multipliers, which I just told you is the Q length. It doesn't even have to do anything. It just looks at its Q length and solves this optimization problem, which is just U prime x equal to P, right? Okay, and the difficult part sometimes can be this. If the network is very complicated, the interference constraints could be large, and this could become a problem of solving a max weight independent set. This could become a max weight independent set problem, which is of course very, very difficult. And so in real life, if you look at 802.11 and all this, we have some distributed algorithms. So basically random access algorithms somehow approximate this, right? So this is the really challenging part. Okay, so people are willing to give up on capacity and other considerations to make the algorithm really simple to implement. So real wireless networks use some, just transmit with some, I transmit, and if I fail, then I wait for a random amount of time, transmit again, and so on. And those are sort of can be viewed as approximate solutions to the max weight independent set problem. Which, I mean, so there's also some beautiful theory behind this, as I mentioned. I'm not talking about it today. Any questions? Okay, so that's the basic algorithm. So the key insight is Lagrange multipliers are essentially Q lengths, or in other words, Lagrange multipliers divided by the step size are just Q lengths. So if you know the Q lengths, you know the Lagrange multipliers for all practical purposes. Okay? Of course, one other minor thing I should mention here is that, of course, mu A is a fraction of time link A is activated, but you don't know that. You don't need to keep track of it. All you do is just look at the indicator function at the current time instant to see whether a link is activated or not. You can just replace this by mu by this indicator function, and still the algorithm works. In a sense, I'll mention what it means. So I'll give a theorem. So I'll tell you in what sense it works. But you don't even have to keep track of the fraction of time a link is activated. You just simply look at the instantaneous activation state of a link. And so this is truly the Q length. This is previous Q length plus arrival rate minus whether an indicator function which tells you whether the link is activated or not. Okay? So the whole talk, my part of the talk at least, is just one slide. I think if you understand this slide, I think you've understood the entire talk, and you can go to sleep, which is, so if you have a constraint of the form y less than or equal to x, okay, to make a connection to the vast literature in applied probability, in particular on queuing theory, every constraint of the form y less than or equal to x can be thought of as a q, where y is the arrival rate and x is the departure rate. Q is stable means on average y must be less than or equal to the average value of x, otherwise the Q will be unstable. So satisfaction of a constraint is the same as testing whether a Q is stable or not. So there's an entire literature in stochastic networks, applied probability literature, which tells you what algorithms one should use to stabilize Qs. It turns out it's exactly the same algorithms that they can be completely equivalently viewed as numerical techniques for solving optimization problems. That's one of the key insights of this line of work by, as I mentioned, a number of us in this area. Okay, so you can sort of leverage, work on queuing theory and leverage work on optimization and sort of mix the two up. Okay, and you can come up with many beautiful algorithms for many, many examples, and I think we'll hear about some of them today. Okay, and there are, yeah. What constraints? Tight constraint, is that what you said? Yeah. Good question. So I'll tell you what the theorem says. Yes, yeah, so exactly. So how close, the approximation error that you get in solving this optimization problem, of course, it'll become more and more exact if the constraints become tighter. If the constraints become tighter, queuing theory also tells you if the arrival rate becomes exactly equal to the departure rate in a real queuing system, of course, the queue length will blow up. So there is actually a trade-off, and I'll mention that in a second. Is that your question? Or okay, okay. So the main thing I want to mention at this point is that arrival rate less than or equal to departure rate basically means that this condition is satisfied or not. And what you have in real life is that you don't have the left-hand side and you don't have the right-hand side. You have noisy samples of the left-hand side and the right-hand side. And that turns out to be enough by making a connection to what is called stochastic approximation theory. Okay? But that's a good question. What happens if y becomes equal to x? Because basic queuing theory tells you that if the arrival rate becomes equal to the departure rate in a queuing system, the queue length will blow up to infinity, right? And so that cannot happen. So therefore, there must be some connection between how large the queue lengths are and how accurately you're able to solve the problem. Okay, and I'll mention a theorem in this context. So, but before I do that, let me just talk about a more general formulation. Here I sort of took the case of two links. You could think about it more generally. You want to maximize the sum of the utilities of all the users in the network, subject to the constraint that user i's transmission rate must be less than or equal to the fraction of time that the link that it uses is activated. Okay, so I'm going to assume that each user just goes over only one link. Of course, we'll get to a multi-hop problem later on. So let's say each user goes over just one link, then xi must be less than or equal to mu I, but the mu's must satisfy some abstract capacity constraint. This C is typically in the form of a convex hull of some discrete set of points. I won't get into it. But basically, the set of links that can be activated, you can think of them as, if you associate an indicator function with each link, there's a set of links that can be activated, can be represented by a binary vector of ones and zeros. So the capacity region is simply the convex hull of this. Okay, but anyway, that's the easy part. So I want, and it's sort of not really germane to what I'm talking about, but this is how the general optimization problem looks like. And you can just simply close your eyes and just do this blindly. Use Lagrange multipliers, add the constraints to the objective. Okay, and the Lagrangian decomposition holds again, and then the optimization problem for each x becomes separate. And then there's a max weight algorithm, which is a function of the Lagrange multiplier. And the Lagrange multiplier is calculated. You don't need to calculate the Lagrange multiplier. It's just simply the queue length. Okay? Scaled by epsilon. So here I put the epsilon here, but that's the same thing. So the Lagrange multiplier is replaced by epsilon times the queue length. Okay? So it's many things. One is it allows you to solve the problem, but also the neat thing about when we discovered this stuff was that this is an easy way to understand. At least I find it very difficult to open a book on computer networks and understand what this various protocol stacks mean, and why did they design congestion control algorithms? Why did they design medium access control algorithms? Why did they design routing algorithms? It turns out that all of these just turn out to be just a Lagrangian decomposition. Okay, so that's the beautiful part of it, and everything can be interpreted as numerical solutions to a optimization problem. Okay, of course, to actually prove that it does something useful, you need probability in this context, and you can prove a theorem like this, which says that the expected value of the sum of the utilities when the system reaches steady state, xi infinity here refers to the system in steady state, is close to the optimal solution. If it is close to the optimal solution, then the queue length will be of the order of 1 over epsilon. So there is also a fundamental trade-off. If you try to push the system to operate close to capacity, okay, then the queue length will blow up. And this is something that everybody knows in lots of contexts. I mean, that's why you allow people to take bathroom breaks when they're answering phone calls. If you don't allow them any break at all, you operate the system at full capacity, the amount of work that people have to, in call centers, for example, when you call and complain that your product is not working, whatever, people set it up so that there are times for breaks. Otherwise the queue length will just simply blow up, and I actually have seen this at Bell Labs when I was working. So there was I won't name the consulting company. There was a consulting company that came to Bell Labs. This was in the early 1990s, where basically they said they actually went to a call center and they looked at every operator, and then they looked at how much time they're working, and they looked at, on average, how much work they require, and they said that there is a big gap, 20% gap, so you should cut down the number of people by 20%, and then AT&T implemented this. AT&T had like 20 data centers, and they consolidated into 2, one in Denver and one in Atlanta. And then they actually ended up paying more money because they were paying overtime all the time, because people were working, because it's like, now you have rho equal to 1, arrival rate equals departure rate, and the system was always overloaded. And so they ended up making, spending more money. So basically, what I'm saying is that this fundamental limit cannot be violated. So you can solve the problem in a distributed fashion, but the penalty you'll pay is that the queue length will become large. Yeah. Yeah. Function of what? Good question. I don't think so. Not in a single link context, it doesn't. In a multi-hop context, I think it may depend on the maximum number of hops in the network. Yeah. This one? It won't be exactly, because of the fact that, okay, so I haven't told you where this expectation comes from. I haven't introduced a probabilistic model. So what we'll have to also take into account is that when you solve this optimization problem, for example, for each user, if X turns out to be 1.3, let's say you have to send 1.3 packets this time instant. You cannot really send 1.3 packets. Either you can send 1 packet or 2 packets. So there's an approximation there, right? And that we model by randomness, and so there will be some variance associated with all of that, and that'll show up here. So it won't just be exactly the solution to the original convex optimization problem. But what I'm saying is here there will be some order. Here there will be some parameters here that also depend on the variance and so on. Yeah. But maybe if you let the variance go to 0, I don't know. We'll have to check whether that works. But it's a little subtle because of the fact that as epsilon goes to 0, you have an instability issue with the queuing network or the queuing system. So that has so it's not. I'm not sure that there is smoothness there for you to be able to conclude that as epsilon goes to 0, you'll get exactly the original solution without any. My guess is that it'll be some small quantity, little o of 1, but I don't think that it'll be exact. Yeah. Mm-hmm.
Let's say I'm interested in some marketplace and I'm trying to map the variables X and mu to a marketplace.
Mm-hmm.
If I think of X, so the I index is some type of agent, maybe X is the rate at which that type of agent is allowed to enter into the market.
Mm-hmm.
Mu is something to do with how the market is bringing people together and
Clearing it, okay.
clearing it up.
I would think so, but I have to look at as long as you can set it up as an optimization problem like this, we can always do this. Yeah. One has to look at the specific model to see if it makes sense to set it up like this way. Yeah. I think Lav Varshni and a bunch of people have done something like what you're saying. Yeah. Yeah, and the proof is you consider appropriate Lyapunov function and look at its drift from one time instant to the next, and then you have to look at it carefully. So it's a long, complicated proof, but basically the idea is not very difficult. Okay. Okay. So in the remaining less than 20 minutes that I have, I just want to mention applications to other contexts. So that was motivated by wireless networks. Of course, the hardest thing today is data centers. So it'd be great if we can apply these to data centers. And in the context of data centers, you have what are called switches. Switches are devices that interconnect many servers. And what I understand is that now people are able to build giant switches that interconnect many, many computers, like thousands of them, for example. Okay. Maybe I'll skip this. Well, okay, I guess I'll keep it. So a data center network can be thought of as you have a network which is interconnecting many servers, and the physical constraint is that at each time instant, each computer can send one packet to another computer or can receive one packet from another computer. Okay, that's it. Okay, and a scheduling algorithm is one that decides who is transmitting to whom at each time instant. Okay, that's what a scheduling algorithm is. I find this interpretation relatively easy to understand. So the idea here is that if you think of the queues in the network as being arranged in the form of a matrix. So for example, this queue contains all the packets that need to go from server 1 to server 3. Okay? And this queue contains packets that need to go from server 3 to server 2 itself. Okay? So, so in this context, the physical constraint in the data center is that you can only serve one packet from each row and one packet from each column. So if you touch one of the queues in a row, then the other queues cannot be touched. Okay, so you cannot serve the other queues at the same time instant. Okay. Of course, you can also view this as a bipartite graph. And here, instead of arranging the queues in the form of a matrix, I'm drawing the queues on the edges, right? And the fact that you can only serve one queue in each row and each column basically means that at each time instant, you can only select a matching in this graph. Okay? So packets arrive to this graph, but when you go to remove it, you can remove only one packet each from the edges of a matching. At each time instant schedule is a matching. And so the same max weight algorithm works. I mean, there's no so before the constraints were imposed by wireless interference constraints. This is nothing but an interference constraint. Basically says that if this link is active, this link cannot be active. There's no difference between a wireless network and a switch. So in fact, it turned out that 1992, Tassiulis and Efremidis had done this work. And then 96, 97 time frame, other people had discovered that the same algorithm works for switches too without realizing there was an earlier paper by Tassiulis and Efremidis. And then everybody realized it's all the same thing. It's just a special case of the original algorithm due to Tassiulis and Efremidis. Okay? What we have given is simply an optimization interpretation of that algorithm. So in this context, of course, the solution is much simpler. It's a max weight matching algorithm as opposed to a maximum independent set, max weight independent set problem in the context of wireless networks. So I think probably most of you know what a maximum weight matching is. So in this graph, for example, we want to find the matching with the largest weight. So this turns out to be the maximum weight matching. You remove one packet from each edge in the maximum weight matching. And then now this becomes the new set of weights. And if I don't want to show edges with zero weights, then basically this is what the new graph looks like. Okay. Same algorithm works. I think that's, so Sivateja, so I want to mention that at this point, so one can ask about optimality issues. Is this a good algorithm? So we motivated it from an optimization perspective. Could ask the question, is this a good algorithm from the point of view what a user perceives in this network? One metric is throughput. What is the rate at which you're able to transfer packets into this network? And it turns out the max weight algorithm maximizes the throughput of the network. So the second question, which is probably more important in practice in certain contexts, is whether the delay experienced by users is the smallest possible in some sense. Okay, and this is a question that's been extremely challenging to address, and Sivateja will talk about, and I think Jamming has some really nice recent work on this topic, but I guess you're not going to talk about this. Yeah. But so there's some very interesting open questions still here in terms of can you minimize delay, for example, does this algorithm minimize delay? And that's not totally clear whether this algorithm does or not. We don't have a resolution one way or the other, although there are modifications to the max weight algorithm, for example, perform really, really well. That's Jamming's recent result. So any questions before I move on to the ad placement example? Okay. So the next example I want to mention is online advertisement, which can also be sort of solved using the same framework. This is work we did many years ago, so I don't know if you search for shoes on Google, probably doesn't look like this anymore, but this was done about 7 years ago or so. So, so the idea is that, a customer is searching for something, and then you want to place ads when the customer is searching. And each company that wants to place ads, like Nike might have said, don't use more than, I don't know, $5 of my money every half an hour or something like that. So there's a budget constraint, which I'm going to assume here is in the form of an average budget constraint that's given by each company to Google, to the service provider. And many advertising slots are available. Okay, so there are two things that a company specifies. It says that every time somebody clicks on my ad, I'm willing to pay 5 cents to Google. And you might also say that I don't want my budget to exceed something. The budget, here I'm going to assume the average budget doesn't exceed something. Okay, so the goal is to place ads in such a way that Google might want to place ads in such a manner that its revenue is maximized. Okay, while respecting the budget constraints that companies like Nike and Adidas has provided it. Okay? This again is a max weight problem, right? So here, the left-hand side are shoe companies, right-hand side are advertising slots. So there are many advertising slots here. For example, you can place the ad here, 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 and so on. So there are shoe companies here, advertising slots here, and you have to find a matching at each time instant. You have to decide whose ad you're going to place in which time slot, except it's not the number of nodes on either side is not the same, but it's nevertheless a bipartite graph. Next time instant you might do this, for example. Okay. So there are many things to take into account. For example, if you place, for example, Nike is offering 25 cents every time, or maybe not 25 cents, maybe 5 cents every time somebody clicks on their ad to Google, and I go and say that I'm going to start a new shoe company and I'll give you 50 cents to place my ad on the top slot. You may not do that, and Google may not do that, because the probability with which somebody clicks on my ad, Srikant shoes, is very, very small compared to Nike, right? So they want to take into account, they of course have to take into account the click-through rate, the probability with which somebody will click an ad when it is placed in a certain slot, right? So there are many parameters like this. So I won't belabor the point, but the point is that you can set up this thing as a linear program. So here are a lot of variables, so don't ignore them. You want to maximize the revenue to the companies, such as Google, while making sure that the budget constraint that Nike and Adidas and Puma or whoever has given you is not violated. Now, each of these is a constraint of the form x less than or equal to y. Each of them can be represented by a q. And so the same max weight algorithm should work. Okay? Let me skip a few slides and just tell you what the algorithm is. Basically, at each time instant, you keep track of a virtual queue. There is no queue here. The queue here is basically the budget shortfall or the amount by which you have exceeded the budget. So this is something, it's a counter that you have to keep track of. So it's not really a queue in the sense that computer scientists think of queue as a particular data structure. You don't need any data structure, just a simple counter that keeps track of whether you have fallen behind in the budget or you're ahead in the budget. And those will be the weights. Okay, so before the Lagrange multipliers, which were the Q lengths, were the weights. Here again, the Q lengths are the weights, but the Q length is just simply the budget for shortfall or whether you're ahead in the budget. Okay, so it turns out in this particular case, the weights are of the form something like 1 over epsilon minus QG, where 1 over epsilon is like the step size in the optimization algorithm. So the Q length is very large, becomes very large, then this weight will become negative, and it inhibits certain ads from being placed. Which makes sense. I mean, if you're starting to exceed somebody's budget, then basically you're going to say, okay, I'm not going to place that person's ad anymore. Okay? So just working through the way exactly I did it for the context of wireless networks, the solution comes up very easily. Okay? And you can, in this context, you can allow for whether you're going to, what do they call it, free disposal, or whether you can decide whether you want to be nice and allow people to exceed their budget, or if you want to be very strict about it, all of those can be handled here. Okay, but in a probabilistic sense. I'll get to what cannot be handled later on, but you can, in some sense, you can. In an average sense, average budgets can be handled in this framework very easily, but some things cannot be handled, and I'll mention that in a second. Okay. So far I've talked about what's called the max weight algorithm. The weight of a link, or the weight of, conceptual link, the context of advertising, there is a sort of, you can think of a conceptual link between a person who wants to place the ad and the advertising slot. The weight of the link is related to the queue length, okay? The weight can also be what is called the back pressure, related to something called the back pressure. And that comes up in certain contexts. Suppose in a wireless network, instead of, in the example that I took, instead of just having 2 users, suppose there's a third user which traverses both link A and link B, okay? Then on this link, the decision is not simply to transmit whether to keep the link on or not, but when the link is on, you have to decide whether user 1's packet should be transmitted or user 0's packet should be transmitted. So the decision becomes more complicated, right? So before I had a variable mu A, which told you the fraction of time that link A is activated. Now you have to say, you have to have a variable that says mu A0 and mu A1, where mu A0 is the fraction of time link A is activated, and you use it to transmit user 0's packet. And mu AN1 is the fraction of time link A is activated, but you're using it to transmit user 1's packet. So as a result, the optimization problem looks more complicated. So there are more variables, mu A0, mu B0, mu A1, mu B2, which basically tells you the link and the user. So mu B1 tells you, mu B2, for example, tells you whenever I activate link B, what is the fraction of time I'm using it to transmit user 2's packet? And of course, the interference constraint still remains. Now, if you go through the Lagrangian decomposition, the optimization problem, the max weight problem, becomes associated with link A, associated with Lagrange multiplier mu A0, associated with the decision variable mu A0, there is a difference. There's a difference from, it's not just simply the queue length, it's the queue length across this link. So it is, I have a picture somewhere, yeah. So basically this is the weight of a link. The weight of a link is simply the weight is the queue length at the head of the link minus the queue length at the tail of the link. Okay, so this quantity is called the back pressure. And, and it makes sense. So if you're thinking about it in the context of a road traffic, for example, if there is if you're driving on a long highway, or not a long highway, long road with multiple traffic lights, if traffic is backing up further down the path, okay, then you're not able to move forward, right? That is basically the idea behind the back pressure algorithm. The weight of a link is this Q minus this Q. If this Q becomes large compared to this link, suppose compared to this Q, then the weight of this link becomes negative, and that link will not be activated anymore. So this is what's called that's why it's called the back pressure algorithm. Somehow sort of there is a pressure moving backwards. And if there is downstream packets waiting, then you won't be pumping more packets into the network. You know that will only cause congestion. In fact, it's precisely what people are using actually in the context of self-driving cars, and people are also trying to redesign traffic lights. The same algorithm, identical algorithm, is being used to decide how often to turn on and turn off lights. So if there's a back pressure, if you see that there's a lot of cars going this way, going through multiple lights, if further down there is congestion, then you start increasing the amount of time the green light is on further, whereas you decrease the amount of time that the green light is on here. So you throttle the amount of traffic going that way. Okay, so that's the intuition behind the back pressure algorithm. I just want to mention 2 caveats. We can handle average constraints. So so suppose the total power used by battery should be less than or equal to something, we can handle that. But if you write it in the form of total energy, then we can't handle it. Okay? So if similarly in the advertising context, I mean you can approximately handle it, but the theory is not very precise in this context. I mean what I'm saying is it cannot guarantee strict budget constraints. So you can give some other types of guarantees, but not strict guarantees. So for example, in the advertising context, if Nike or Adidas will have a contract with Google saying that don't use more than this much of my money this month. So it's an average type of budget. But a private person, suppose you're trying to advertise a book, for example, they'll just give, I want to spend $100 on this, and that's it. Once $100 is spent, you can't place my ad anymore. That cannot be exactly handled in this framework, but of course, there are other models where, in particular, I know the work by Feldman, Kurula, and Mirokny I guess from Google, who have written a sequence of papers using competitive ratio models where they can handle strict budget constraints, although that has its own limitations. But it's just for completeness, I want to mention that can be handled in slightly different models. Another problem that cannot be handled is virtual machine placement. I think I'm running out of time. So basically, the idea is that instead of going through the virtual machine placement problem, it's basically what's called vector packing. So you have a bunch of vectors, and the vectors have to be placed one on top of each other so that the sum of the vectors doesn't exceed the capacity of a box. And you can also pose these kind of problems and get a max weight solution. But if vectors arrive and depart, and they arrive and depart asynchronously, packets, for example, here, in everything I've talked about, I've assumed the time is slotted. A packet arrives and it departs, but everything happens in a time slot. But if different packets take different amounts of time to process, then you can't immediately relate it to an optimization algorithm, and this is an open problem. Okay, so how to handle it? In Siviteja and I, in one paper, and Siviteja and I in Lei Ying in another paper, we have some solutions, but they're sort of kludgy solutions. I think a beautiful solution is waiting to be derived for this problem. Okay.
Sounds like Airbnb's problems with booking running over multiple days.
Yeah, or just even the simpler problem of how to assign tables when you're making reservations in a hotel, because you don't know, people are not eating for exactly half an hour, and that creates a problem. Yeah. So this is my summary. As I mentioned, I talked about things that are like at least 10 years old, maybe 7 years old, some of them. But what we will hear about in the rest of the talks is sort of more interesting and newer developments in the context of data centers and ride-hailing platforms, connections to machine learning in the context of crowdsourcing or other online service platforms. And you need complete, techniques beyond just this basic connection to optimization is needed, and I think you will hear more about it in the next few hours. That's it. Thank you.